People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
The void has always intrigued mankind. The concept of no concept defies the laws of human reasoning to such a degree that we have no choice but to pursue it. But ancient Assyrian, Norse, Judeo-Christian creation stories, and even our own scientific inquiries have one thing in common: creation from nothingness. But is it really nothingness? Ancients used the term chaos, and, although to some chaos has become synonymous with bedlam or randomness, it has much more to do with the timeless myth of creation of form from the formless. So how does chaos take form? And is there meaning to be found in the apparent arbitrariness of chaos? Or is it a void that defines what we think it means to be? All of this and more on this episode of Breaking Math. Episode 2, Wreaking Chaos. With us we have...
I'm Charlie Shipley. I'm a freelance journalist and former writer for the Daily Lobo.
This is Amy Lynn, joining you again. I'm a public school teacher in mathematics.
I'm Hannah Butler, and I have a Bachelor's of Science in Mathematics from the University of New Mexico.
And Gabriel, you're going to start a little bit with talking about physics and determinism?
Exactly. Actually, this is really cool. I have the privilege of opening our episode on chaos with my own little story. I have a story about actually what got me interested in physics and math in the first place. This is a story that for a very long time I've been wanting to include on the podcast. So here goes nothing. Years ago, I was going to school to become a teacher, actually, and I was in a science class just for teachers. and I had a chapter that I was assigned to review. This chapter was on Isaac Newton. And after reviewing this chapter, actually, I thought it was so fascinating. It was so well written that I almost changed my major right then and there to physics. My hope is that for our listeners and for our readers who follow the website, they might have their own story about what got them really interested in physics. So, back to the story. The entire chapter was on orbits. And of course, it described the story that many of us know about Isaac Newton and how, the apple drops from the tree, and he wonders, what is it about the earth that draws the apple toward it? And of course, he formulates his idea of gravity by saying, if you were Isaac Newton and you were to drop an apple from your hand, it would fall down. However, if you were to throw the apple, it would travel a distance and then it would fall down. So let's pretend that you didn't have somebody like Isaac Newton, but rather you had a Superman who was much stronger than Isaac Newton. Let's say that he were to pick up that apple and he were to chuck it much harder and much further. It would travel much further along the surface of the earth before hitting the ground. Now, pretending, of course, that you didn't hit a mountain or a tree or a building, how far would it go before it would hit the ground? We know the earth is curved, so think about it. As that apple is traveling and as it falls down, it can fall as the earth curves. It's going to go a very, very far distance if you have someone like Superman throwing it. Hypothetically speaking, if he threw it hard enough, it would fall as the earth curves, and it would come back around and smack him in the back of the head. Of course, the whole purpose of this analogy is to describe, in effect, what an orbit is, and exactly what the moon is doing. The moon is falling toward the Earth. It's just that it has an angular momentum with it. The force equals the gravitational constant times the mass of the two bodies, the Earth and the moon, divided by the
Square of the radius.
Yeah, the square of the radius. It's a very simple formula. And in this single formula, that describes the movement of the moon around the Earth. That describes
It's the square of the distance between them.
Thank you.
Yeah.
I'm sorry. Thank
There
you.
you go.
Thank you very much. Thank you. I got into my storytelling mode here.
Mm-hmm.
That simple equation explains the movement of the moon around the Earth around the sun. That's every body in the universe. Suddenly.
So what does this have to do with chaos?
Okay, here's what this has to do with chaos. In short, with Isaac Newton's math, we get what's called determinism, where if you know the momentum of an object and the initial directions, you can already predict the trajectory. In short, you can know the future of where it's going.
The destiny.
You can know the destiny. So on one hand, that's an incredibly cool tool. You're like, wow, I can now, draw on a chalkboard like a cannon, and I know exactly where the cannonball is going as long as I know the initial mass and the initial conditions, etc.
And you know that a million years from now.
Yes, yeah, exactly. It's the same. Now, there's a darker side to this mathematics. There's a darker side to physics. The term we're dancing around here is determinism. And philosophically, this is actually very, very uncomfortable. The idea of determinism is, okay, so if you know the initial momentum of something, and if you have enough information about the initial state, do you then know the future? Is there no such thing as free will? That's a very, very uncomfortable topic to broach.
And as I recall, you were going to talk about the three-body system.
Yes, absolutely, absolutely. Because it's not so simple. That is where we introduce the concept of chaos, where you have three bodies all in orbit, and things are not as neat and tidy as we would like to have them in Newton's math.
All right, Gabe. So let me stop you there for a moment, if I may. As somebody who understands nothing about what you just spoke of, you had me at darker side and determinism. So let me put it in terms of popular culture. Are you telling me that there is a mathematical equation that could have predicted whether or not Luke Skywalker would have joined his father on the dark side of the Force?
Let's say that we knew everything about Luke Skywalker, every atom in his brain, the direction they were going, and we knew them perfectly, which is impossible by the uncertainty principle, but that's for another episode. Yes, we would know if he joined the dark side. We know everything about Luke Skywalker's future. We would know when he ate a hamburger, on what day, how many hamburgers he ate 1,000 years in the future, and so on.
Then that's the daunting thing, is the only thing about determinism is it's just a matter of we don't know or that we can't know. And that's a really interesting concept.
Anna, do you have anything to add about the three-body system?
Right. So, a lot of people started looking at the three-body system once they had figured out how to deal with the two-body system. And so kind of the main guy, the guy who contributed a lot to chaos, is Henry Poincaré. So he was studying the three-body system, or I guess more generally the n-body system, with just kind of an arbitrary number of bodies. It happens to be impossible to solve. Big thing that Poincaré did was that he kind of approached the problem in a more qualitative way rather than a quantitative way. So rather than trying to predict the exact positions of bodies in the future, he asked the question, something like, is the solar system going to be stable forever, or at some point will the planets fly off into infinity? And so this was kind of the first glimpse that people got into chaos, was working on that three-body problem. And this is kind of where they encountered things like sensitivity of initial conditions.
And that, for most listeners, is the butterfly effect. Does the butterfly flapping its wings in Peru set off tornadoes in southern China? And we'll talk a little bit more about that later, because the question is a lot more nuanced than a lot of people think. So right now, what we're going to do, before we talk a little bit more about chaos, we have to acquaint our listeners with a concept called a vector field. And the example that I came up with as a simple example is the hair on your head. As the wind blows, the hair goes in different positions. If you look at the hair as a bunch of arrows, it shows the vector field of the wind around your head.
Actually, this is a really, really important topic. In my research, both as an electrical engineer and my graduate program, vector fields are a big, big thing. So I think the hair on your head is actually a really good analogy.
It is.
Another good analogy, the one I always use, is basically if you had a whole bunch of windsocks in a field, and a turbulent wind would blow. That's also a vector field, because you've got all the arrows and you see where things are going at any given point. So
Now imagine we have the windsocks. We have an array of windsocks in 3D, just windsocks everywhere. Basically a whole three-dimensional field of windsocks. You could tell where a particle would be going by following the direction of the windsocks at any given time. That's the cool thing about vector fields. They let us know the ultimate destiny of a point that starts. Wind, fluid, motion, all of these are described very well by vector fields. And we need vector fields to describe limit cycles. Now, Hannah, would you like to describe limit cycles for our listeners?
Maybe before talking about limit cycles, we want to introduce attractors. So an attractor is basically something, it could be a point or it can be a set of points, a line, a circle, that kind of everything around it is eventually going to move towards. So a limit cycle is basically circular or some sort of closed orbit that everything around it is eventually going to spiral into.
For our listeners who would like to have a visual representation of a limit cycle, go to breakingmathpodcast.com/applets.html.
due to the nature of this episode and due to the nature of getting our listeners acquainted with chaos, there may be a little bit of jumping around. It may be, dare I say, chaotic. Having said that, just okay, so we're following along here. So in a chaotic system where you've got a lot of moving parts, when you talk about something like a limit cycle, okay, so that's basically the track that...
Well, let's say we have
Is it the track that the windsock moves on?
a little bit, yes. A limit cycle and a dust devil for a point might be the way that it moves around. That's a limit cycle for a dust devil.
Why is it called limit cycle? Again, this is just for our folks who have never heard of the term.
Well, because okay, imagine we're stirring a cup of coffee. If you put a grain of sand in the cup of coffee, you're going to be displeasing whoever is going to drink that coffee. But what the sand is going to do is it's going to go towards the middle until it goes to the center. In this case, the limit cycle is a point. It's called a limit cycle because where you start has sometimes nothing to do with where you end up and where you end up going.
So is it basically the parameters in which a given event occurs
In a chaotic system.
Not
right?
in
necessarily.
a chaotic system?
So before we really talk about a limit cycle, I think we need to address what a limit is. And that we can't really do that in super technical terms because it is confusing in technical terms. But a limit is something that as you go on, as time goes on, as the variable gets large or as it gets very small, you approach some limit. There's some value that you approach. So a limit cycle is what our system of equations, or if it's points that we're discussing or recording, it's what we're approaching. So that limit cycle could be any shape. It could be 3-dimensional, it could be 2-dimensional, but that is what we're approaching.
A good example might be if you take 1/2 of something, then add a quarter to it, then add an eighth, then add a 16th, and keep adding half of what you added before, the limit of that will be 1. Just as a very simple example limit, would you say?
Yeah, that's a good example.
So a limit cycle is what a piece of dust in the wind will approach doing. It'll approach going around a certain circle. But sometimes the cycles are strange in cases like the Lorentz attractor. Hannah, would you like to introduce why the Lorentz attractor was conceived in the first place?
Really quick, the Lorentz attractor doesn't have any limit cycles.
Yeah, it doesn't have limit cycles, but it's an example of an attractor and when limit cycles basically fail.
Yeah. Okay, so the Lorentz attractor kind of came up when Edward Lorenz, he was kind of studying the weather and atmospheric patterns. And as far as atmospheric patterns go, there's kind of an infinite number of variables that we can consider. And so what he did was he simplified it as much as he possibly could. And he just kept simplifying it until he kind of reduced it to 3 variables.
And for those who would like to know exactly how he reduced it, you can find that on breakingmathpodcast.com/papers.html.
When he simplified it, he still found that, when you started at a certain point, that basically you'd still get this kind of chaotic behavior over a long period of time.
And as I recall, the story of him discovering the butterfly effect with his attractor was an input error. He started with an input and had a certain amount of decimal places, but he transposed 2 of the decimals. And then when he graphed it, he found that the system went wildly different than it did when he started. So he found out that there was an extreme sensitivity on initial conditions. Since you could imagine this sort of sensitivity in real life, just imagine a butterfly flies into your car, distracts you, you crash into the side of the road. That's an extreme example, but this is what sensitivity on initial conditions means.
So you said inherent fragility in situations. Does that mean that all situations are inherently chaotic?
Not all situations are inherently chaotic.
Or most situations have the inevitability of chaos? Is chaos an inevitability in anything?
It is not known. It's a very recent field. It's not known exactly what causes chaos. It's known that it happens when you have more than 3 variables. In a lot of conditions, that's a gross oversimplification. However, an example of a system that's not chaotic is a cannon. You fire a cannon, you fire it a little bit more, you get a little more distance. You fire a little less, you get a little less distance. That's not a chaotic system.
But wouldn't variables in, say, the gunpowder or the condition of the cannon or the condition of the ball, wouldn't those fall under chaos?
They could fall under chaos. The more variables you add to the system, the more likely it is that you will run into chaos.
Yeah, I think with standardizing things, then that also limits those variables, or at least it attempts to. But I mean, that's actually a very good question. Again, just for identifying what's chaotic versus what's not. And actually, the whole story of Lorentz, that's a fascinating story. I love that story. You actually touched on this before. So again, you mentioned that he was making a simulation, or he was running a simulation, and the simulation was for the weather, correct?
Yes,
Okay.
It was a simple simulation. It assumed that all weather was homogeneous, basically, and only had 3 variables.
Okay, yeah, so basically, yeah, his extreme oversimplification of it, only 3 variables. Now, really, there's a lot more than 3 variables with weather when you think about it. There is, gosh, how many can we name off the bat? There is temperature, there's humidity, there is
Time.
there's time, there's what else?
There's pressure. There's viscosity. Look, just anything in the fluid dynamics equation.
That's a very complex system. So really, he just whittled it down to just 3.
But even whittling it down to these variables, he still found very complex behavior.
Okay. Now, tell me again, this part I find fascinating. This is what really led to the whole story about the butterfly effect. So, in his simulation, you mentioned something about was it he misplaced 2 decimals?
Yes, he wrote, when he was putting it into the computer, he wrote it down a little bit wrong, and it was a bunch of decimals into the thing.
Okay. Now, if I remember correctly, it was a very, very, very insignificant decimal. Like, was it? It wasn't even the 100th place. It was like
it was probably in the 10,000th or 100,000th place. It was very small at this point.
So then, in short, you run the simulation, right? And he maybe misplaced, 100,000th, a very, very incrementally insignificant digit in this little simulation on weather. Then you run the simulation, and then the next day he looks at his results, and they are wildly different than what he thought of.
And that's why weather prediction is so difficult. It's a chaotic system. Anything more than a week and a half really is completely unreliable.
Wow, that's just amazing. That shows how significant this fragile system is. That's if you want to talk about some pop culture examples, things like Back to the Future, where you've got small changes, will have massive effects.
I think that's right, but I don't know. I mean, I'm sure Jonathan here could find a mathematical model of Marty McFly sleeping with his mother and negating his own existence. And upon further introspection, that's actually some math I'd like to see. But, I think a more pertinent example, particularly because the author of the source material was so passionate about mathematics and science and economics and all that kind of thing, would be Jurassic Park. Anyone who's ever read the original novel, as well as the sequel novel, The Lost World, will find that between the chapters are fractal curves depicted as if done by computer simulations. And, of course, for those not aware, Jurassic Park had introduced a character named Dr. Ian Malcolm, who billed himself as a chaotician rather than a mathematician, played by Jeff Goldblum. And he used the mathematical concept of chaos to illustrate why and how Jurassic Park would not and could not work. He summed it up in the eloquent line, "Life will find a way." And when we look at the events that happen in that movie, we will see that I think the inherent fragility of situations comes into play very startlingly, not only with the tour group itself, but even as far as the beginning of the tour, where the Dilophosaurs fail to show up. Then you have the sick Triceratops. Then you have the weather coming into play. Then you have unscrupulous employees playing with the security system. So I think the movie itself is actually a very appropriate example of chaos.
And one thing that you brought up, and this is what we're going to discuss a little bit next, is that although there may be sensitivity on initial conditions, a butterfly is as likely to create a tornado 100 years from now as it is to prevent a tornado 100 years from now. And not only that, but the flaps of a butterfly's wings cannot change the frequency of tornadoes, only the order in which they occur. If Universe A has tornado, hurricane, tornado, hurricane, hurricane, tornado, Universe 2 might have 3 tornadoes, a hurricane, and then 4 more tornadoes. That's the way in which chaos works, and it's a lesser-known property of the butterfly effect.
Now, Jonathan, something you mentioned is Universe A and Universe B. Now, this may be too inside baseball or too off the rails, but what about the parallel universe or many worlds theory? Do alternate universes or the theory or possibility of alternate universes affect the mathematics of events in this universe?
That's going off a little bit on a tangent. What I can say about that is that the inaccuracies inherent to just measuring any material, the uncertainty principles, which says that the more you know about momentum, the less you know about position, means that any chaotic system will have inherent unpredictability just because of that. Rabbits and foxes have a relationship which is too well known to be restated, but we will anyway. Foxes eat rabbits. But how many rabbits? When there are not many rabbits, the foxes starve. The rabbits see this as an opportunity and multiply. In response, the foxes prosper, and the yearly cycle continues. Yearly, because rabbits have mating cycles annually. But it turns out that this is not the whole story. When you start with certain proportions of foxes to rabbits, it could take 2 years for the cycle to repeat, and with other proportions, it could take 8 years for the cycle to repeat, and so on. This is the reason why you have phenomena in nature like cyclic plagues. The cyclic nature of events is an essential and as yet unproven property of chaos. Empirically, however, it has not been with exception, and that is why it is included in the mathematical canon. If you had a proper chaotic system controlling a Ouija board, for example, there's a starting position for the pointer that will spell out every word, every sentence, and indeed every book ever writable again and again until the end of time. This is the nature of chaos. It preserves information, but only the information that it is given. How is this different than determinism? How do we have to change the way we look at things because of this new worldview? Now we're going to talk a little bit about the rabbits and foxes example. What's the name for that technically?
The Lotka-Volterra model.
And how is that an example of a limit cycle?
So starting at certain points or starting at certain population, a certain initial population of rabbits and foxes, they manage to kind of keep each other in check. Whereas when we get too many rabbits, the foxes will prosper and they'll start eating all these rabbits, but then they'll run out of food. And then the foxes will start to die off. And then in response to that, the rabbits will start to multiply and their population will grow, and we'll kind of have this balancing act between rabbits and foxes that just goes around in a cycle again and again and again. And that kind of cyclic behavior is an example of a limit cycle.
So could it be said that the cycle of evolution and survival of the fittest is just a giant limit cycle?
It's full of limit cycles. The way that they interact is highly nonlinear. Evolution in life is an example of a nonlinear system. It's a very good example of one because just looking at humans and the fact that we're able to simulate any nonlinear system means that it's nonlinear. But attractors are essential to the way that we look at chaos. An attractor it's an object that has a certain limit that it goes around. And I'm going to play a sound example of an attractor known as a Lorentz attractor.
Okay, so do we want to explain exactly what it is that our listeners just heard?
That was a Lorentz attractor by Edward Van Halen.
Well, what that was is
Edward Lawrence, thank you.
Is an example of a chaotic system, and the reason why it's chaotic is because when you take two very similar starting points, they end up in completely different positions, and we'll play an example of that right now.
What do the different tones represent for our listeners?
The amount of a square wave is the x direction, the volume is the y direction, and the frequency is the z direction. So if you go in one direction, it goes ooh. If you go in another direction, it goes ooh. And you go in the other direction, it goes ooh. So those are the three directions.
So in the first sound that we heard, it was just kind of one sound, and it sounded kind of weird, but it was just one sound. But in the second, you could hear them start at slightly different kind of tones, I guess. But as you played it for longer, you can hear that they're starting to move away from each other.
Yes.
So what do those two different tones represent?
Those tones represent different points in 3D space. And you can hear that they have the same, they go around the same sort of cycles, but they go around them in different orders at different times, different distances away from the center. It's a sonic representation of a strange attractor.
So for our listeners, the Lorentz system, the Lorentz equations, it's a system of three differential equations, which we won't get into that necessarily right now, but it's actually three fairly simple equations that, given certain parameters, we have a behavior that is described in three-dimensional space, so X, Y, and Z in mathematical terms. So we have a point moving in space, and it's circling around it depending on the parameters. The classic example is that it's kind of circling around two distinct centers, but it's rotating around each of those. And so what you've created is something that describes in those three dimensions, given those three parameters, the location of that.
Fill your summer with the sun-kissed sweetness of Amigos Refreshers. There's strawberry acai, blueberry dragon fruit, and mango passion fruit, each a tropical delight. So skip the hot coffee and amp up your day with the plant-based natural caffeine and fruity flavor fusions in an Amigos Refresher. These cool thirst quenchers are just $3.99, or there's a mega 32-ounce size for $4.99. Recharge with the bold, fresh flavor of an energizing refresher at Amigos.
Line as it's growing in space.
Yes, and for our listeners, a simple example of a differential equation is driving. When you have the wheel at 2 o'clock, the wheel is not moving, but the car keeps turning. You move the wheel back to 12 o'clock, and the car goes in a straight line. In this case, the position of the car is a differential equation of the position of the wheel. If you were to somehow make the wheel tied to the speedometer, you'd get a real sort of differential equation. But yeah, that's the sort of complex system we're talking about.
Can I give my example of what a differential equation is?
Absolutely.
So a differential equation in simplest terms is it's an equation that contains a variable and its derivatives. And if you think about it in real examples, that the derivative of position is velocity, the derivative of velocity is acceleration. So if I had an equation that talked about the velocity and the position of my car, that's a differential equation.
And of course, the derivative of the position of the car is like you said, on the speedometer. It's the rate of change. That's what a derivative is.
Right.
So in that second sound, at the very beginning of that, how did those two tones differ from each other?
They differed by a factor of 0.0001. Just to give you an example of how small that is in terms of the attractor, they go from about negative to positive 30.
Okay, so they're really, really, really close together.
Very close. The fact that we could hear them says a lot more about how sensitive our ears are than how different they are.
But yeah, so the point though is that they were really, really close together. But then as, time went on, they started sounding really, really different.
Yes.
Why is that?
It's because the Lorentz attractor is a chaotic system. It's sensitive to initial conditions. An example of a system which reduces to the Lorentz attractor is multiplying by 2 and then truncating when you get more than 1. To elaborate, start with a number like 0.2. You double that, you get 0.4, 0.8, then 1.6, but then you subtract 1 because it's more than 1. You go to 0.6, and then you go back to 0.2. So then your cycle there is 2, 4, 8, 6, 2, 4, 8, 6. And every single cycle on the Lorentz attractor has an equivalent cycle using this doubling and truncating by 1 example.
Right. So that first one, the sensitivity to initial conditions, where if we don't start in exactly the same place, if we have two guys that are starting at slightly different places, they're going to move away from each other at an exponential rate over time. Along with that, we also have that chaos has aperiodic long-term behavior. We're never going to repeat the same pattern ever.
Well, we could repeat certain patterns, it's like the natural numbers versus the irrationals, but in general, right, it's completely aperiodic.
Yeah, very rarely are there periodic trajectories in a chaotic system.
And like we talked about in the last episode, there's a lot less rational numbers than there are irrational numbers.
So does someone want to describe the difference between periodic and aperiodic, or just tell us what periodic is?
Periodic is like A, B, A, C, B, B, A, C. A, B, C, B,
Yeah, so you lost the pattern already.
I lost track.
So
That's
something
not
that is
periodic.
periodic is something that repeats periodically, right? So
Yep.
it's something that has a periodic pattern. So something that is aperiodic, something that's chaotic, is going to be something that has no discernible, or it may have a pattern, but it's a non-repeating pattern, right? I think chaos doesn't even have any kind of discernible pattern, right?
In general, no.
Okay.
Not at all.
Because I know that
why it's
irrational
chaos,
numbers, right? But irrational numbers can have a pattern so long as it doesn't repeat.
I think that says a lot about the world that there are more irrational numbers than rational ones. Just let y'all chew on that for a minute.
Yeah, right. That was profound.
It really does, though. But that's a topic for our math and intuition episode.
All right, so chaos. So a chaotic system is what we generally discuss, right? So what are other important characteristics of a chaotic system?
So we have the sensitivity to initial conditions. We have the aperiodic long-term behavior. A chaotic system is always deterministic, which means that if we know exactly where we start, we're always going to be able to predict where it will be anytime in the future. And that's it.
But you need to know exactly.
You need to know exactly. Exactly.
You can't have an approximation and be like, that's good.
Right. So because of that sensitivity to initial conditions, if we don't know exactly where we're starting, then that point that's not exactly where we want it to start is going to move away exponentially fast.
Real quick, I wanted to point out that we had started off this discussion with the idea of the cold, hard determinism of Isaac Newton's math, and then we went to chaotic systems. Now, chaotic systems are deterministic in fact. It's just that with the
Not in practice.
Okay, and can you clarify
In theory.
how? Okay, so then for our listeners, again, if they're trying to understand this and if they're trying to describe, I'm hoping to get some clarification with how it's deterministic in theory but not in practice.
Sure, it's deterministic in theory just because we can simulate it on a computer. I mean, that's just one kind of like piece of evidence that points towards it if we didn't already know it. If you know exactly where it starts, you can continue it. However, if you don't know, okay, let's take the weather, for example. Let's say that we had a measure of every component of weather at every square foot on the entire planet. Within 3 weeks, we would not be able to predict what the weather turned into because it's a chaotic system. It depends so much on initial conditions that even an approximation as good as one measurement per square foot would not be enough to tell us about the fate of the weather.
Okay, that's mind-blowing. So, wow, literally. So you had it was a radar? One radar per square foot?
One radar that measured, humidity, everything.
Okay, so one radar, and if you could measure every single variable, the maximum you could go is 3 weeks?
I mean, the maximum you could go really, to any appreciable degrees, about 3 weeks.
Okay. So then I guess my question is, we still do live in a determinate, from a philosophical perspective, we still do live in a deterministic universe. We just don't know what that destiny will be.
Essentially, yes. I mean, there's a little bit of philosophical disagreement about what the uncertainty principle means, but that's a discussion for another time.
Okay. I just wanted to clarify.
I'd be interested to know how closely chaos and philosophy relate to each other.
Very, very closely.
Yeah.
Yeah, it's...
Math and philosophy are completely interconnected.
Brilliant question. Also, it's a phenomenal plug to other episodes. Math and consciousness, that's going to be
Math
a big
and
one.
logic.
Yes, math and
Oh,
logic.
yes. Yeah, we have our huge episode that'll be going in several episodes. Consciousness, we have an entire episode on proofs in philosophy coming up pretty soon.
Nice.
One of the things that I find interesting about a chaotic system is that we've kind of given up on realistically trying to estimate, right? But we still can predict weather patterns, right? Mm-hmm. And the way that we do that is by modeling chaotic systems and looking at probabilities and looking at what's happened in the past and what conditions have led to others. And I find that pretty interesting.
Yeah, we know there's going to be a hurricane season, for example.
Right.
We keep mentioning the weather when talking about chaotic systems, but what about the political system? Could that also be? Now, I'm not saying any names. I'm not naming any names. I'm not speaking of any particular thing that just happened on November 9th. But theoretically, you could relate the political system to chaos as well.
Any nonlinear self-referential system lends itself to chaos eventually. Good example. And we have a few other examples of chaos. Imagine you're at the state fair, riding a Ferris wheel, when all of a sudden there's a torrential downpour. But the cloud's only about 20 feet wide and is raining only on the highest spot on the Ferris wheel. The power, because of the shoddy construction, cuts out, and some of the carts under the downpour start filling with water. They're leaky, so some of the water leaks out. The Ferris wheel starts turning their way because they're heavier. However, the more Ferris wheel turns, the more carts get their chance to be filled with water, and it starts turning the other way. Now, our question for you is this. Which direction does the wheel turn ultimately? The answer, which may not surprise you at this point, is that it'll turn back and forth forever, aperiodically, in a way that is essentially unpredictable. 1 degree, or even 100,000th of a degree of distance between two different starting positions could mean the difference between being at the top and the bottom of the Ferris wheel in a very short period of time.
Something really interesting about that situation is that Lorenz's simplified atmospheric model perfectly models the Ferris wheel problem.
Yes, and it wasn't the motivation, the fact that people criticized his model for being too unrealistic and having nothing to do with reality.
Mathematicians always hear that.
So again, I believe we said this earlier, but just to clarify for our listeners. So even Lorenz's simplified model with 3 variables, we still have no idea how effective that is in terms of modeling weather. Like we don't know if it's completely ineffective, and we don't know if it's effective. Is that right?
Yeah, I mean, I know that certain configurations of beta and alpha correspond to perfect convection and so forth, but I don't know what those are. I don't know enough about fluid dynamics to comment on that.
Interesting.
We wouldn't be able to understand it anyway, so that's okay.
That sounds like a challenge. So, now that we have a few examples of chaos, does anybody else have any examples they would like to bring up of chaos, chaotic systems in general?
I'd like to pose a question. Earlier we were joking about Back to the Future and, Marty McFly. Now, one of the things that I believe Hannah was saying about the Lorenz attractors was you had to know the precise conditions at any given time.
Yes.
Now, earlier Gabe had mentioned Back to the Future, and this actually relates more than I realized now, because in that movie, they knew exactly when the lightning bolt was going to strike at 10:04 p.m. to send Marty back to the future. Now, I thought I knew where I was going with this, but just to kind of put a bow on it, is that something that's in the realm of possibility in the real world? Can we actually know exactly when something is going to happen down to the minute, or is that a figment of Hollywood?
That's a figment of Hollywood. I'll tell you why. I've done the Lorenz attractor with 0.000, like 20 zeros and then a 1 of difference, and it does always split up, no matter how close they are.
Sorry, guys. I thought I had.
The problem is we can never possibly know everything, right? That we are but mere humans, and we can't possibly know every possible condition in our universe. That's why weather is the prime example of a chaotic system, because we can't ever know exactly everything.
The uncertainty principle states that there's always going to be something that we don't know about the position of something if it's moving quickly and vice versa. It's xp minus px equals h bar.
Y'all got
No,
that?
that's Heisenberg.
Mm-hmm.
Yes.
That alone brings up a huge amount of philosophical questions about physics, which we will get to on a future episode. Open up a Russian nesting doll and you'll find a smaller one. Open up that one and you'll find a smaller one than that. If this process could go on forever, you'd have a fractal. A fractal is anything that you could zoom in on and continue zooming in on and always see detail. In this way, chaos and fractals are very similar. In fact, you can make fractals out of many chaotic systems very easily by graphing starting positions. One property of many fractals is self-similarity. Take trees, for example. A branch looks like a miniature tree, and each branch on that looks like a smaller branch. This is not an essential property of fractals, however, but fractals are found everywhere in nature, from coastlines to the circulatory system to rivers and clouds. If chaos is a language of nature, then fractals are the words in which it is written. So how do we read those words, and what can we learn from doing so? So, fractals. How can we make sense of what fractals are? Of course, they have infinite detail, but what does that essentially mean?
So as far as chaotic systems go, so chaotic systems do have attractors, but rather than the attractors being like a fixed point or a limit cycle, the attractors are fractal sets. So all of these trajectories are attracted to a set that is a fractal.
The attractors is essentially
Right, so
the behavior.
that butterfly shape of the Lorenz attractor, that's a fractal, because you can zoom in as much as you want and it'll keep like repeating. It's just like infinite amounts of folding and folding. And
So it's still a chaotic system, but it's one that repeats a behavior rather than repeating a specific place. Like it repeats a pattern, kind of. Well, I mean, like my introduction to fractals was not in the pictures, it was in the fractional dimension aspect. And so I never really saw the connection between chaos and fractals. So is it I guess by behavior I mean is that self-similarity. So it continues to make the same shape.
Yeah, so as you zoom in, it's just going to be the same thing over and over and over again. It's just going to it'll have structure at arbitrarily small scales.
So in that sense, the fractal, the shape is the attractor.
The shape, yeah. Mm-hmm.
And here we have an auditory example of a fractal. This is just the Mandelbrot set, which we'll describe in just a minute. And we'll play this and we'll be right back.
So again, can you describe what those sounds represent?
Yes, the pitch represents the y-axis, the time represents the x-axis, and basically what this is a picture of the Mandelbrot set made into sound. And the reason why I played it is if you listen back, there's a lot of little tiny details that you could hear. Now, any representation of a fractal that's finite cannot represent that fractal. However, you can see that it's becoming a fractal. And one way of doing this is by just showing you how to draw a very simple fractal. It's called the Sierpinski triangle.
Well, let me talk about that.
Okay.
So the Sierpinski triangle, or the Sierpinski gasket, it's a representation of one of the coolest math moments I ever had. That if you think of a triangle that is filled in, so you have a whole triangle and you cut out the middle fourth, right? So you cut out a triangle from the middle, you take it away, and then you continue to do that to what remains. So I take out the middle fourth of the 3 triangles that remain, and then I take out the middle fourth of all the little triangles that remain. That if you do that infinitely many times, what is left, you have taken away all of the area, right? This is the nature of infinite. But we've left all of the end lines, right? And all of the points where it connects. What is left is equivalent, it's dense, right, which is a mathematical term that we may describe later, but we've taken away the area, so it no longer has dimension of 2, but we know that it has dimension greater than 1. So that is where we get the term fractal, a fractional dimension. We've just created something that's fractal that has a dimension between 1 and 2.
Yes, imagine you have a yardstick and want to make it twice as long. It's simple, it's now 2 times as long. Now, let's say you have a yard and you want to make it so that you have to walk twice as far everywhere in between the yard. The yard is now going to be 4 times as big as the yard was before. And if you have a room where you want to make it twice as big in every dimension, it's 8 times as big, and so on. Now, let's think about that Sierpinski triangle that Amy just described. When you double it, you get 3 times as many. You don't get 4, and you get more than 2. Remember, 2 is a yardstick, and 4 was something 2-dimensional. And it turns out that it's around 1.58 dimensional. Wrapping your mind around fractional dimensions is, of course, daunting, but that's the way of measuring it. And you can even measure the coastline of England this way.
This triangle is just nuts. Actually, while you guys are talking about this, I am here at the Breaking Math website, and I'm looking at the applet right now. It's absolutely mesmerizing watching this Sierpinski triangle form itself. I could just look at this forever. And I got to say, I'm sure I'm not alone in this, but among our viewers, I'm not the only one who cannot wrap my mind around 1.58 dimensions. That doesn't compute. I only think of dimensions in whole numbers. Sorry. That's just mind-blowing. That's given me a lot to chew on.
That's why it was one of the most mind-blowing moments of mathematics for me. That mine was actually the Cantor set, which is the between 0 and 1 dimensions.
Oh wow!
And the proof that it has to be between 0 and 1 was just so amazing to me.
Yeah, and for our more mathematical minded listeners, it's log 2 divided by log 3.
There you go.
Again, talking about parallel dimensions, when you think in terms of numbers that small, that to me is good evidence for the many worlds theory.
It might be. And we'll totally discuss that on the physics episode. And real quick, I do want to give an example that Hannah brought to my attention of a fractal that is not self-similar. Divide a square into 9 pieces, take away a random piece of that square. Now with the remaining 8 squares, divide each of those into 9 pieces and take a random piece out of every single one of those. And keep doing that with the resulting squares. You're going to get something that has an infinite amount of detail but is not self-similar at all.
When we say the word fractal, what you're probably picturing in your mind is the Mandelbrot set. That's probably what you imagine. It's probably the most famous fractal in the world. It's a fairly simple system. It's a simple construct to create it. But before computers, we could never visualize it. And so that's what was really impressive to me about fractal theory, is that it very much came before we could see where it was going.
But as soon as we could see where it was going, we were like, holy crap.
It's so pretty.
Exactly. Yeah, and
Wow.
it sounds weird too.
Can we, real quick, go into a little bit of history of the Mandelbrot set?
Well, it's if you're mathematically minded, imagine the complex plane. Basically, that's where y is the imaginary component, x is the real component.
So that's a big topic in and of itself. We are all accustomed to the real number line, right? I think we've all learned that in elementary school. We think about positive and negative numbers being centered around 0 on the real number line. That the complex plane, which was something that was fairly, it was really scary at the time. They didn't want to admit that complex numbers existed. So we introduced that we are no longer thinking of numbers as one-dimensional, that the line, the real number line, was not sufficient for the mathematics that we wanted to do. So they said, you know what, I need to be able to take the square root of a negative number. I'm just going to call it I. And that number, it's a number. It's totally legit. And they made fun of him and said, yeah, those are imaginary. You're full of crap.
And you could take the square root of I. It's just square root of 1/2 plus square root of 1/2 times I. Or square root of 1/2 minus square root of 1/2 times I, I'm pretty sure.
But again, I is the square root of -1, which all throughout school they tell us you can't take the square root of a negative, right? That was just a fact that we were told. The mathematician who said, I need to be able to take the square root of a negative number, that it's really important to electrical engineering and the way that circuits work.
Even
That
quantum systems.
Right, that imaginary numbers do have to exist. So I prefer to call them complex numbers. We call it the complex plane. And really all it means is that we're going from a real number line, which is one-dimensional, into a complex plane, which is two-dimensional. But we're still just talking about numbers.
Yes. Of course, it has the property that if you take b times I and multiply it by c times I, you get negative bc, because it's b times c times I, and I times I is -1. But just for a quick mathematical description of the Mandelbrot set, what it is, imagine you have a point. What you do is you take a number, square it, add c to it, and then keep doing that over and over again. If it goes to infinity, then it's not part of the set. If it settles on a certain number, then it is part of the set. And that's just our technical description. It's not necessary for an understanding of fractals in any way, but it's interesting.
Something that goes back to the point that Amy just made, perusing the Wikipedia entry on imaginary numbers here. And one of the things it says is originally coined in the 17th century as a derogatory term and regarded as fictitious or useless.
I mean, even Descartes thought that negative numbers were fictitious and useless. The original Cartesian coordinates did not have a negative component.
My students still stand by that statement.
I
so.
kind of want to go back to my math classes and say I think all of this is fictitious and useless. I demand that we redo my grades.
So the Mandelbrot set is in the complex plane. It's a very simple equation that you take, and it's something called an iteration. So you take the previous term, you square it, and add a number to it, and that is the next term, right? And so you continue on that pattern, and that produces a set of numbers which creates what we all recognize as the fractal, the Mandelbrot set.
Yeah, and it's interesting how much just the study of fractals and chaos in the last century has kind of completely changed the way that we view systems in general. Bifurcation diagrams, which Hannah mentioned earlier, are an iterative process. Well, they happen because of an iterative process. But if you look at the original paper, he thought that it was going to be something very easily predictable. If you Google bifurcation diagram, you'll see how complex they are. Yeah, it's changed the way that people view everything. There's tons of movies called The Butterfly Effect. Everybody knows about the butterfly effect. Everybody understands that fractals are a thing. Yeah, it's changed the zeitgeist. Now we explored the consequence of chaos, the properties of fractals, and the nature of these complex systems that make up our world. And the field is new, less than a century old. As the systems we use to analyze them grow more complex and our understanding of these processes becomes more nuanced, the influence that these sorts of systems will become better understood, and the ways in which we can use them to build our world will only become more fruitful. I'm Jonathan.
And I'm Gabriel.
And this has been Breaking Math. Today we had on Amy. And Amy, would you like to plug anything?
I work for the Public Academy for Performing Arts. It's an APS charter school. Go charter schools. Go Papa. We're raising money to get a performing arts center at our school to serve a need, as charter schools do, to promote performing arts in New Mexico and Albuquerque for these wonderful students. Support your local charter schools.
We also had on Hannah today. Hannah, would you like to plug anything?
No.
Math is awesome. That is awesome.
Math is awesome, says Hannah. And Charlie, would you like to say anything?
I'd like to thank you all for having me, and this has been a very informative discussion. I want to thank you for indulging my attempted insertions of popular culture into our discussion of mathematics, and I look forward to hearing the final podcast.
Awesome, man.
Thank you for listening to Breaking Math, and check out other Generation Listen podcasts at KUNM.
Save big this summer with great deals, all in the Baker's app. Get red, green, or black juicy seedless grapes for $1.88 per pound with a digital coupon. Then buy 2, get 2 free delicious 12-packs of Coca-Cola, Pepsi, or 7-Up, all with your card. Shop these deals at your local Baker's, less than 10 miles away. Or tap the screen now to download the Baker's app to save big today. Baker's, fresh for everyone. Prices and product availability subject to change. Restrictions apply. See site for details.